Sure. Welcome viewers. Today we will discuss about the higher discrete mathematics. This mathematics, it is the language which connects the our language with the computer language. The most important and the most demonstrating examples in the higher discrete mathematics are the recurrence numbers. Today we will discuss about the recurrence relations. These recurrence relations in the mathematics, they are very helpful in the software programming of the computers. But their invention was too early. Let us start from the 1202. Leonardo di Pisano, it is an Italian mathematician. First of all, he wrote in his book Liber Abeti about the recurrence relations, and it is also called the Fibonacci numbers because the nickname of the Leonardo is Fibonacci. You can see this number, you can see these numbers, Fibonacci numbers on any website present on YouTube. They are very interesting, but here we are concerned with the mathematics and we have no fun in this mathematics. Just we have to understand what are the recurrence relations and how to deal with this problem. That is the main deal of our meeting. Well, you can find so many websites on the YouTube saying fun with the recurrence relation, fun with the golden numbers, but I don't think there is any fun in this topic. It's somehow typical, containing the different theorems for the different questions. That is the complexity of this topic. So let us start with some Fibonacci numbers which he gave in 1202. Let's see this recurrence relation 1, 1, 2, 3, 5, 8, 13, 21 and so. It was the first recurrence relation given by the Fibonacci in 1202. See, first number 1, second number 1, then 1 plus 1 is equal to 2. It is the second number. Then 2 plus 1 is equal to 3. 3 plus 2 is equal to 5. Or we mean to say that every number in this recurrence relation is the sum of the two previous numbers. So we can write this sequence Fn is equal to Fn minus 1 plus Fn minus 2. Here we have taken n is greater than or equal to 2. Similarly, we can generate the sequences with n greater than 3, 4 for any numbers. Each number in the sequence or in the recurrence relation is the sum of the previous two numbers. Now, these numbers were not generated automatically. How did the Fibonacci introduced these numbers? Let us discuss about it. Then we see what is the magic and how they are related with our nature. These golden numbers, these are called the golden numbers. They are very close to the nature. We shall see after this. He gave the first of all the one example that was on the breedings of the rabbits, or we call it rabbit breeding problem or the rabbit and the Fibonacci problem. Rather, this discussion or this problem, rabbit breeding problem, is impractical, but that was the first problem discussed by the Fibonacci in his book. Let us consider one pair of the rabbits. One pair means one male and one female. They are alone any island. There is no one else them, the pair of the rabbits. Now, we apply the condition. We say the male plus female, that is the one pair. One pair of rabbits. there is a one pair of the rabbits, one male and the one female. That this problem we are discussing about the generating of the recurrence numbers, or we can say Fibonacci numbers or the golden numbers. How the Fibonacci generated the numbers. Let us consider a one pair of the rabbits, male and female, living on a lone island. Then we put up a condition. What? They can breed after 2 months. They can breed after 2 months. Then at the end of third month, they reproduce new young pair. That is again male and female. These are the conditions put up by the Fibonacci, that this pair will breed after the 2 months, and at the end of the third month they will reproduce new young one, and the young ones are also in pairs. It means one male and one female. Now let us put all these things into the table and see how the generation or the Fibonacci numbers generates. Let us see here there are months, then reproducing pair, at least 2 months old. In this column, we will keep only those pair of rabbits which are at least 2 months. It means 2, 3 or more than 3. Here the young pairs not more than 2 months. Young pairs not more than 2 months. Now, again I repeat the conditions. We will start in the first month. Say it is a single pair of the rabbits, one male and one female. It is on a lone island. Conditions are they will reproduce. They will start breeding after 2 months and they will reproduce at the end of the third month. Then most important condition is that the pair which is 3 months old, after every month, after that means in 4th month, in 5th month, they will start reproducing. Let us start from the first month. On a lone island, it is a pair of the rabbits. On the first month, it is only one pair, because they will start breeding after 2 months. In the second month, we see again this rabbit is alone, so we don't write it here. This rabbit pair is alone. No. In the second month, this pair will start breeding. And in the third month, this pair will start reproducing. It is the first pair, and say it is first generation. It's a first generation. We say, let us call it N1. Now it is 1 month old, it is new pair. Then in the 4th month, what we see, this old pair will produce again one pair. That is say N2, and one pair is also it is 2 months old. It is 2 months old. We see in the 5th month, that is it is the oldest pair. In the 5th month. It will reproduce one pair. No, this pair is now 3 months old, and it can also reproduce one pair, and one pair, no, it is 2 months old. Let us see how the sequence is generated. In the first month, there is only one pair. Second month, only one pair, one pair, one pair. In the third month, two pair. And in the fourth month, fifth month, it is 5 pairs. Similarly, if we will produce this table, we will get the numbers 5, 8, 13, 21, 31, and so on. Rather, this problem was very impractical. Then he modified this rapid building problem with the problem of boss and the buffaloes. You can see them on any website available on the YouTube or on the Google. These are called the golden numbers. Why these are called the golden numbers? Now we shall see this. If we summarize all these numbers, we say f of 1. First sequence is 1. Second number is also 1. Third number 1 plus 1, 2. Fourth number 2 plus 1, 3. And fifth number of the sequence is 5. And so on. We will continue increasing this problem. Then at last we generalize fn is equal to fn minus 1 plus fn minus 2 for n is greater than or equal to 3. Remember this condition. I have taken n is greater than or equal to 3 because the rabbit pair, they start reproducing at the end of the third month. If you will see in the certain other books or on the other material, they use the breeding of the pair at the first month and reproduction at the end of the second month, and they will write here n is greater than or equal to 2. But I have taken breeding at the end of second month but reproduction at the end of third month. That is that you will see certain difference in the certain books or on the certain websites, but they are the same. They will start the sequence with 0, but I don't consider the 0 here. I considered it started from the 1. 1 plus 1, 2. 3 plus 2, 2, 1, 3. 3 plus 2, 5. And 5 plus 3, and so on, 8. These golden numbers, they are very close to the nature. How? Let's give you some examples. The flowers in our nature, they have petals. They have petals which follow this sequence approximately, not every time but approximately. How? You can find the flower with one petal. You can find the flower with the 2 petals. You can find the flower with the 3 petals. But flower with 4 petals, they are very rare. They are very rare, or they are not available. Or you can say the petals which we count the petals, they may be the sepals. Then 5, you can find the flowers with the 5 petals, but flowers with 6 petals and again 7 petals, they are very rare in nature. And moreover, you see the pollen pattern of any flower. Pollen pattern of any flower, it's starting from the inside. If we, with the help of a lens or a microscope, we count these numbers, we will see they also follow this number of the recurrence relation, that is the golden number. How? They are real, they are related to the nature. You can see on any website available on the YouTube, Fibonacci and the in nature, Fibonacci numbers and the nature. You will see the different patterns and different flowers, names of the flowers even, and their patterns, their bifurcations, each and everything. But in nutshell, I want to say these golden numbers, they are closely related to the nature. Second example, I say these numbers, they form the spiral. Now, what is the role of spiral in this topic? We say that our galaxies, they are in the universe. We have at least 10 raised to the power 11 galaxies in this universe. What is their shape? We know only the shape of few galaxies. Other than our galaxy is in the pipette shape, like this. It is called the Akash Ganga. But we find that some other galaxies, they are in the spiral form. Now we see how this spiral is related to these golden numbers or Fibonacci numbers. Let us draw a small spiral and we see how can we extend it with the help of a graph, or you can make it with the help of a computer also. Let us see. It is in square, or you can see a graph paper. So first we divide it into two sections, divided into equal section. Then this part again equal to the two equal sections. And now this part again equal to two equal section. Now this part into the two equal section. And this part again equal to two equal section. You can use the graph simply. Let us start here. Is the number one. Here is the number one. We start with from here. Number one. One box, and it is one box. No, one box plus one box, that is equal to two box on your graph paper. 1, 1, 2, then 2, 1, 2, 1, 3, 3, 2, 5, and 5, 3, 8. Now, if we start joining these numbers like this, 1, 2, 3, 5, 8, and next number is 13, and after that 21, you will see it will form the spiral. It means the nature also follow the rule of these the golden numbers. So they were not generated accidentally, but the consideration was too strong of the Fibonacci that the numbers are very close to our nature. Again, we see take some other example of these Fibonacci numbers, that we use a term golden ratio. What is the golden ratio? It is used in architect or the civil engineering. They use it very often. Golden ratio means if we divide a line into equal two parts, A and B. Here A is greater than B. A is greater than B. Then A plus B. It means sum of the both parts divided by the larger part. That always comes to be equal to 1.668 approximately. It is the golden ratio. Now, we see how these numbers they are related with this. Let us see this number, say 3 by 2. Why we have not taken the first two numbers? Because the regeneration or reproduction has started at the end of 3 months. It means our sequence or recurrence always start with n-2 months. Then 3 by 2 is equal to 1 by 5. After that, say 5 by 3. 5 by 3, that will come to be 1.666 at 7. It's approximately. Then 8 by 5. 8 by 5, that you will find 1.6, and then 13 upon 8, that is equal to 1.625. ratio of the Fibonacci numbers is same as the golden ratio, approximately. Accept these two values. As we proceed, if in further in the golden numbers, we will see that the ratio of two conjective golden numbers is always very close to the golden ratio. It is the very old concept used by the mathematicians in the architect engineering or in the civil engineering. So that is the basic introduction of the recurrence relations. You can see the more examples in your booklets or on any website available on the YouTube. We are concerned with how to deal with these recurrence relations or how to solve these recurrence relations. So these recurrence relations, they seems to be simple. Their presence is very soft. They seems to be funny, but I don't think anything in the mathematics is funny. It's always serious. The solution of this recurrence relation is typical problem. Why? Each problem follows the different theorem. According to your booklets of the IGNOU, we will discuss about the recurrence relations.